the third interstellar visitor has arrived. It's real, it's moving fast, and it's forcing scientists to rethink what's possible in our solar system. Tonight, we're diving deep into 3I/Atlas, what it is, what we truly know, and why NASA's silence might be the most strategic sound you'll ever hear. But before we get into the science, let me ask you something. What if this frozen wanderer has been traveling through space longer than our entire solar system has existed? What if the ice we're observing right now froze around a star that died billions of years ago? That's not science fiction. That's the reality we're dealing with. And by the end of this video, you'll understand why 3I/Atlas isn't just another space rock. It's a time capsule from another corner of the galaxy. 3I/Atlas, officially designated C/2025 P1, is the third confirmed interstellar object ever detected by humanity. The first was Oumuamua in 2017, which shocked the astronomical community with its elongated shape and mysterious acceleration. The second was 2I/Borisov in 2019, which behaved more like a traditional comet and gave us our first clear spectroscopic data from an interstellar visitor. Now we have Atlas. And it's proving to be just as fascinating, if not more so. It was discovered in 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, a network of powerful survey telescopes that scan the skies continuously from Hawaii and Chile. These robotic observatories are designed to detect near-Earth asteroids that might pose a threat, but they occasionally catch something far more exotic. Here's what makes it interstellar. Unlike the thousands of comets and asteroids that orbit our Sun, 3I/Atlas has a hyperbolic orbit. In simple terms, that means it's not gravitationally bound to our solar system. It came from somewhere else, passed through our neighborhood, and will leave forever, never to return. Think of it like this: our solar system is a roundabout, and most objects go in circles. But 3I/Atlas? It entered the roundabout from a highway, took one loop, and is now exiting onto another highway leading to deep space. At its closest approach in late October 2025, Atlas skimmed near Mars's orbit, about 1.5 astronomical units from the Sun, before heading outward again at nearly 35 kilometers per second. There's absolutely no threat to Earth, but there's an extraordinary scientific opportunity, a rare chance to study material from another star system up close. To put that speed in perspective, if you could drive a car at 35 kilometers per second, you'd circle the entire Earth in about 20 minutes. And this object has been traveling at that speed for potentially millions of years. When the story first broke, news outlets around the world ran dramatic headlines. NASA goes quiet about 3I/Atlas. Space agency refuses to comment on mysterious visitor. What is NASA hiding? But here's the truth. That silence isn't secrecy. It's science working exactly as it should. Let me explain why updates come in bursts and then seem to stop. Data calibration. When a telescope captures an image or spectrum, that raw data is essentially meaningless until it's been processed. Background noise must be removed, instrument signatures must be corrected, and measurements must be cross-checked across multiple observatories. This isn't a one-day process. It can take weeks or even months depending on the complexity of the observation. International coordination. Space science isn't done by one agency alone. NASA, ESA, European Space Agency, JAXA, Japan, ground-based observatories in Chile, Hawaii, and the Canary Islands, all of these teams need to compare notes and ensure their data is consistent. If one telescope sees something unusual, others must verify it before it becomes official. Observation windows. Here's something most people don't realize. We can't just point a telescope at 3I/Atlas whenever we want. The object's position relative to the Sun, Earth, and other planets changes constantly. Sometimes it's too close to the Sun's glare. Sometimes it's on the opposite side of the solar system. Good viewing angles. When the object is both visible and properly illuminated, open only occasionally, sometimes for just a few days at a time. Peer review. Before any major findings are published, they go through rigorous peer review. Other scientists who weren't involved in the research examine the data, check the math, look for alternative explanations, and either approve the work or send it back for revision. This process is intentionally slow because the stakes are high. Getting it right matters more than getting it fast. So when weeks pass without headlines, it doesn't mean something is being hidden. It means scientists are doing their job, making absolutely sure that the next headline is accurate, verifiable, and reproducible. In fact, rushed announcements can do more harm than good. Remember the faster-than-light neutrinos that made headlines in 2011? Turned out to be a loose fiber optic cable. Proper science takes time. Thanks to early observations from the James Webb Space Telescope, humanity's most powerful infrared observatory, researchers discovered something truly fascinating about 3I/Atlas. The coma, that glowing cloud of gas and dust surrounding the solid nucleus, is dominated by carbon dioxide, CO2. Not water vapor, which is typical for comets in our solar system, but CO2, along with smaller traces of water, H2O, carbon monoxide, CO, carbonyl sulfide, OCS, and fine silicate dust particles. Why is this unusual? Most comets we've studied, like Halley's Comet, Hale-Bopp, or the hundreds observed by missions like Rosetta, have water as their primary volatile component. They're essentially dirty snowballs with some CO2 mixed in. But 3I/Atlas flips that ratio. It's more like a dirty dry ice ball with some water mixed in. This tells us something profound about where it formed. In any planetary system, there's an invisible boundary called the snow line, or ice line, the distance from the star where it's cold enough for water to freeze. Beyond that, there's the CO2 ice line, even farther out, where temperatures drop below -78 degrees Celsius. 3I/Atlas likely formed beyond its parent star's CO2 ice line, in the outermost, coldest regions of that ancient solar system, perhaps 30, 40, or even 50 astronomical units from its star, in a region comparable to our Kuiper belt, or even farther. It's like peering into the outer freezer of another solar system, chemistry that was frozen solid billions of years ago, and has remained unchanged. A pristine sample of conditions that existed when that distant planetary system was still forming. And here's the mind-blowing part. The light from that parent star may have long since faded. The star itself might be dead. But this fragment of its planetary disk is still here, drifting through our neighborhood, carrying secrets from a time and place we can never visit. One of the most common questions people ask is, how big is it? And the honest answer is, we're not entirely sure yet. Here's why. Estimating the size of an active comet's nucleus is notoriously difficult. The glowing coma, that cloud of gas and dust being vented into space, acts like a bright fog around the solid core. Telescopes, even powerful ones like Hubble, can only measure the total brightness of the comet, not the nucleus itself. It's like trying to measure the size of a light bulb by looking at the glow around it. The brighter the glow, the harder it is to see the actual bulb inside. Current models, based on brightness and activity levels, suggest the nucleus of 3I/Atlas could range anywhere from a few hundred meters to several kilometers across. But most experts agree the actual solid core is likely on the smaller end, probably under 1 kilometer in diameter. But here's what makes it interesting. Despite its relatively small size, 3I/Atlas shows an unusually high level of activity per unit of surface area. In other words, it's venting gas and dust more efficiently than typical comets of similar size. Why would that be? One possibility, its surface crust is thinner or more porous than average. When comets travel through interstellar space for millions or billions of years, they're bombarded by cosmic rays, high-energy particles that can crack and weaken surface ice. This radiation damage might have created fractures, making it easier for subsurface ice to sublimate, turn directly from solid to gas, when the comet gets close to a star. Another possibility, the composition itself. If the ice is mostly CO2 rather than water, it sublimates at a lower temperature, meaning the comet starts outgassing earlier and more vigorously as it approaches the sun. Think of it this way. Water ice is like regular ice in your freezer. CO2 ice, dry ice, is far more volatile. Drop a chunk of dry ice in warm water and it immediately starts bubbling and steaming. That's what we might be seeing with 3I/Atlas. We don't know for certain yet, and that's exactly what makes it scientifically valuable. When 3I/Atlas passed near Mars in late October 2025, something special happened behind the scenes. NASA's Mars Reconnaissance Orbiter, along with ESA's Mars Express and possibly even instruments on the Perseverance rover, had a unique vantage point that Earth-based telescopes simply couldn't match. Here's why the geometry mattered. From Mars's perspective, the Sun was positioned almost directly behind the cameras. This meant the comet was fully illuminated, like taking a photo of someone with the Sun at your back rather than behind them. No shadows, no glare, just pure, clean light. Even better, no atmospheric distortion. Earth's atmosphere, even on the clearest nights, causes stars and comets to twinkle and blur. Mars's thin atmosphere is negligible by comparison, and spacecraft in orbit have no atmosphere at all. The images captured from Mars' orbit would be razor sharp. But here's what most people don't realize. Mission planners had prepared for this months in advance. Every single minute of rover and orbiter time is meticulously planned. These spacecraft have limited power, limited data storage, and limited bandwidth to send information back to Earth. So dedicating precious observing time to 3I/Atlas meant someone very high up in the mission hierarchy decided it was absolutely worth it. And it was. From that Mars observation window, scientists obtained the sharpest views yet of the comet's coma structure, revealing jets of gas shooting out from the nucleus, asymmetries in the dust tail that trace how sunlight erodes different parts of the surface, and even subtle color variations that hint at compositional differences within the coma itself. These observations are still being analyzed, but early results suggest the comet is rotating with a period of somewhere between 6 and 10 hours, and that the outgassing isn't uniform. It's concentrated in specific, active regions, on the nucleus, possibly areas where the ice is more exposed or the crust is thinner. So when people say NASA went silent, what actually happened was this: they collected extraordinary data, and then they paused to make sure they understood it correctly before saying anything publicly. That's not secrecy. That's precision. Tracing an interstellar object's origin is like detective work on a cosmic scale. Astronomers use the object's current trajectory, its position, velocity, and direction, and then run the math backward through time, accounting for the gravitational pulls of the Sun, Jupiter, Saturn, and even the Milky Way's overall gravitational field. For 3I/Atlas, the results are fascinating. The trajectory seems to point back toward the thick disk of the Milky Way, a region filled with older, slower-moving stars. These aren't the young, hot, massive stars you see in spiral arms. These are ancient red dwarfs, old sun-like stars, and the remnants of stars that died long ago. This suggests 3I/Atlas could be a fossil from the early galaxy, potentially billions of years old, ejected into interstellar space by gravitational chaos during the formation of its parent solar system. Here's how that might have happened. When a planetary system is forming, there's a disk of gas, dust, and ice around the young star. As planets grow, they gravitationally scatter smaller objects. Some fall inward toward the star. Others are flung outward into stable orbits. But some, perhaps 10% or more, are thrown out of the system entirely, destined to wander the galaxy forever. Jupiter did this to countless objects in our own solar system. In fact, we're still doing it. Every few years, Jupiter's gravity flings a comet out of the solar system permanently. Now imagine that happened billions of years ago in another star system. That comet, 3I/Atlas, has been wandering through the void ever since, traveling at tens of kilometers per second, crossing distances so vast that human minds can barely comprehend them. And then, by sheer chance, its path intersected with ours. Think about that, a chunk of ice older than Earth itself, carrying chemical fingerprints from a star we'll never see, passing through our cosmic neighborhood for just a few weeks before vanishing forever. It's one of the most humbling reminders of just how big, how old, and how interconnected the universe really is. Every time something from another star enters our skies, the internet ignites with theories. It's an alien ship. NASA's hiding the truth. But here's the reality. Every single observation of 3I/Atlas fits perfectly within the laws of natural cometary physics. Its chemistry, its light, its movement, all tell the story of ice and rock, not metal and machines. Oumuamua mystery taught us something similar. It sped up slightly as it left the solar system, and people thought it had engines. But comets do that all the time. When ice turns to gas, it pushes the comet forward, a natural rocket effect. 3i/Atlas isn't hiding secrets. It's revealing truth. Because the real wonder isn't in fantasy. It's in the fact that a visitor from another star system is passing us by, carrying material older than our own planet. Mystery sells? But truth, real cosmic truth, is far more profound. Some think NASA's silence means secrets. But silence, in science, means work. Here's how it really happens. Telescopes collect data. Scientists calibrate it. They check, recheck, compare, model, and write. Drafts become papers, papers face peer review, and only then does the world hear the results. Those long pauses between updates? That's not hiding, that's thinking. That's science, breathing before it speaks. In late October 2025, 3i/Atlas reached its closest point to the Sun, its moment of glory. The comet blazed brightest, releasing ancient gases into the void. Now, as it fades into the deep dark again, scientists are racing to capture every last clue. Tracking the changing balance between CO2 and H2O. Refining its true size using light and heat. Studying the dance of dust grains through polarized light. And comparing its chemistry to other interstellar travelers, Oumuamua and Borisov, to map the diversity between worlds. There's no danger to Earth. But there is a danger of forgetting what this object can teach us, about how worlds form, and how material journeys between the stars. 3i/Atlas isn't just a comet. It's a message in motion, a frozen letter from a world we'll never touch. We can't chase it. We can only watch, listen, and learn. And in that quiet, something beautiful happens. Because silence isn't the enemy of discovery. Silence is discovery, unfolding slowly, carefully, truthfully. Behind every pause are scientists calibrating data, engineers scheduling telescopes, reviewers checking equations. And when NASA finally speaks again, it will be worth the wait. Because what they'll say will be true. If a major update comes, a new spectrum, a refined orbit, something unexpected, you'll find it pinned in the top comment, backed by real data. So if you want signal over noise, subscribe, stay curious, and keep looking up.